All right, so I should put the other one. Good morning, guys. Just let me know if you're hearing me and if you're seeing the screen. No, you're not seeing the screen. So let's put this one. Let's put this screen. Deidre, Kay, Nashan, Cherie, Alex, Simone, Bonetta, Alicia, Daniel. You guys are hearing me?
Yeah.
No? Yes, okay. Thanks, Alicia. All right, so the weather is really nice outside. I hope you're enjoying it as much as you can. Welcome to Biostatistics 2. And as you know, Biostatistics 2 will build on the knowledge that you've already have from Biostatistics 1. All right? So you have the foundation already, and we are going to be building on that. So as you already know, we're going to be meeting once per week. Typically, our class is going to be on a Friday morning at 11 a.m. So it's 1 2-hour session per week on Fridays at 11 a.m. Hi, Daniel. The handouts are up here. We have an approximate total of about 12 sessions, and we're going to be looking at various interesting topics ranging from assessing and testing. No, leave this one. Ranging from assessing and testing for normality, data transformation, where you can actually convert your data to an approximate normal distribution if you wish to do so. If you do not wish to do so, you can apply what we call a non-parametric test. So we'll be looking at several non-parametric tests that you may have come across already in the literature. We'll also take a look at logistic regression, where you learn the principles involved in predicting a categorical variable. So when we did multiple linear regression, we were predicting a numerical variable for the, yes, a numerical variable. For this one, logistic regression, you'll be learning to predict a categorical variable. And then the final step we'll make is at reliability. So we'll learn how to assess whether or not the wonderful questions that you have made up for your questionnaire oh God, are good enough to assess what you set out to assess. And that is just one aspect of reliability. So we look at that, and then we will look also at, certain things like how our gold standard, some of the things you've been learning in EPI about gold standard being compared with maybe a new screening tool or something like that. So we're going to look at some of that. Now, just like our previous journey, this course emphasizes data, concepts, and applications, and not so much the derivation of formulae and proof of theory. So we're going to be having a combination of lectures and labs. So guys, from now on, please forgive me. I should have told you to take your laptops from yesterday. Just walk with your laptop unless you are told otherwise, because we're going to be doing them simultaneously, lectures and labs. So there's no specific time set aside for labs like we had in Biostat 1. So basically, that's just a brief synopsis of our itinerary for this journey. And you already have most of this on the course outline. There are no take-home activities for this course, so there's no assigned homework for you. So no take-home activity, be it individual or group. There's no homework, no coursework, so to speak, to be done for this course. There's also no written exams for this course. So there's no mid-course assessment. There's no written final assessment. I'm just telling you all the perks of this course. So the only assessment that you have is, just a conversation with members of the faculty concerning the most significant highlight of this journey for you, meaning your favorite topic that you want to come and talk about. And then after you've spoken about that and we allow you to demonstrate it using SPSS software, then we will talk about a topic that we want to talk about. And you'll also should be able to demonstrate that using the software as well. So Google in the exam. It's not an open book test. So you should study to show yourself approved. As you come and you talk. No, there are no, I wouldn't have done that, Janelle. Would you want me to share your exam with somebody else? No, we're not doing that. So
or maybe you can present and record yourself.
I will not do that. You guys are okay. So what you're gonna do towards the end of the course, we'll give you like a summary of the topics and maybe like some questions for each topic. And you'll be able to, they'll give you practice exam database and you can go ahead and run those and answer the questions. And if we have the time, we can go through, but usually we don't have the time. If there is a slot somewhere.
I choose the topic I want to talk about.
In BIO2 too.
But yeah, I choose the topic prior to coming right?
To the exam? Yeah. So you prepare it. So it's very difficult to fail. If you fail, it means that you really did not study it. The pass rate.
When I asked, then 90% of the persons.
Yeah, people rarely fail. So 90%? No, it's not the same. It's probably about 80 or 75. I've never checked it, but just thinking, I think maybe about 80. But by let's do the pass rate is higher. People rarely fail. Because at least it should be coming in at 50%. You must know your topic. You must know what you have chosen to talk about. So that's the best we can do. All right, so that's really what the course is about. Any other questions? You can bring your formula sheet. No, you don't need any formula sheet. No formula sheet for this one. You don't need any formula sheet. There, so guys, the handouts are already online. No man, for today's class. For today's, well, at least I should say for this topic. For this topic, everything for this topic is already there. So we'll see how much we're able to cover today. All right, so let's start. So this first lecture, or first week, we're going to be looking at approaches for assessing normality. The objectives basically are, we want to understand why it is that we assess for normality. We want to understand numerical and graphical assessments for normality. And then finally, we're going to use SPSS to carry out both numerical and graphical assessments for normality. So software that we're using for BIO2 is still SPSS, so you don't need any new software. All right. So last semester, when we looked at several statistical tests, we noted that many of them required that the variable is normally distributed, or that the population from which you would have taken our sample to assess that variable within that population is normally distributed. So some of those tests that we looked at were the t-test, the ANOVA, and the regression as well, and Pearson's correlation. Wonderful. So we met one or two tests that did not require or have any assumptions about normality, such as the chi-square test and the Spearman's correlation. Now, why do we really need to assess for normality? So first of all, we really need to find out whether or not our data satisfy the assumptions for normality. Why do we need to figure that out? Once we figure that out, then we can confidently apply the appropriate statistical test. So after we've assessed our data for normality, if our data follows a normal distribution, then we can apply the appropriate parametric test. So you remember that word, you've met it before. And if it does not conform to a normal distribution, then we need to apply the appropriate non-parametric test if we do not wish to transform that data. So that's really the most important thing. Now, broadly speaking, there are two broad methods for assessing for normality. We have numerical methods and we have graphical methods. Numerical assessments are based on statistical tests. They are very objective in nature, and some persons, well, not some persons, generally speaking, they are a little bit exacting, meaning based on the numbers that you're seeing, it might be telling you that your data is not normal, but it might not necessarily be so far from being normal that you cannot use a parametric test. So if you were looking comparative, if you were looking on a graph, you could say, oh, but it's not that bad. So you could still use it. So we say that the numerical assessments, they're a little exacting, they're objective in nature. Some of them will involve the use of a p-value, some of them do not. So for this course, the numerical assessments that we'll be focusing on are skewness, kurtosis, Kolmogorov-Smirnov test, and Shapiro-Wilk test. So number 3 and number 4, the Kolmogorov-Smirnov test and the Shapiro-Wilk test, those two involve a bit of hypothesis testing. So these two will be using p-values. All right. Wonderful. Skewness. We've met skewness before. And we know that skewness speaks to a lack of symmetry. So what is symmetry? So in descriptive statistics in Biostats 1, when we described our data, we spoke about central location. So we looked at things like means, medians, modes. And we spoke a little bit about variability. And we know that includes measures such as standard deviation or extremes, variance, range, and so on. Now, skewness is a measure of symmetry, or more precisely, the lack of symmetry. So a distribution or data set is considered to be symmetric if the left and right halves are looking pretty much identical. So for univariate data, meaning, just one variable, if you're just looking at one variable, the formula for skewness is right here. It's the sum of x minus the mean raised to the third power divided by n minus 1 multiplied by the standard deviation, which is s raised to the third power. So the last point is just telling you what the letters mean. So x bar is the mean, so we know that from bias class 1, the mean of a sample. S is the standard deviation, and n is the number of data points, and x just means the individual data points. But you really don't need to study the formula unless you really want to. Okay. The individual data point, all the heights of everybody. So I just means your height, Samantha's height, Jabari's height, Kristan's height. The first is like the first value, the first individual value to wherever. That's all. It's not anything stressful. From I to N, basically. Right. Right. So all the individual values. All right. Now the skewness for a normal distribution is 0. And any symmetric data should have a skewness near 0. If you apply the formula on the previous slide, and for whatever your variable is, so let's say your variable is height, your variable of interest, let's say it's height, and the value obtained is 0 or close to 0, this would indicate that your data is symmetric. If you obtain a negative value, then your data is skewed to the left. So a negative value that's not close to 0. If you obtain positive value, not close to 0, this would indicate that your data is skewed to the right. And then we know that there are some data sets for which we do not have, or we cannot have negative values. So those will always be skewed to the right. Well, the point is not there, but you know that. So for example, like the chi-square distribution, that one is always skewed to the right. So that's skewness in a nutshell. Kurtosis. So kurtosis is a measure of whether the data are peaked or flat relative to a normal distribution. So data sets with high kurtosis tend to have a distinct peak near the mean. So the mean would be somewhere here. You're gonna be seeing a very distinct peak. They're highly peaked. And the tails, they decline rather rapidly. And some sources define or describe this kind of distribution that is exhibiting a high peak as having heavy tails or fat tails. So once the tails are declining so rapidly, they say, oh, these tails are heavy or fat. Now, data sets, and that curve is described as being leptokurtic. So a highly peaked curve or a curve with high kurtosis is considered leptokurtic. Data sets with low kurtosis, they tend to have a flat top near the mean. So the center of the data is pretty flat. And the tails are described as being thin tails. So for the platykurtic distribution, the top is flat, the tails are thin. Now a uniform distribution would be the extreme case. And this is where, if you can imagine it, all the bars on a histogram are at the same height. So this would be an extreme case of platykurtosis, a uniform distribution. So for example, if everybody in here wears size 9, then we're just gonna see that just going there, just uniform. All right, now for univariate data, the formula for kurtosis is here. So this time everything is the same, x minus x bar, except the exponent. So this time it's raised to the power 4. And now we're gonna divide that. So it's the sum of x minus x bar raised to the power 4 divided by n minus 1 multiplied by s raised to the power 4 as well. So that's kurtosis. By this formula, if you're gonna apply this formula to your variable of interest, the kurtosis for normal distribution is gonna work out to be 3. You understand? Good. So if you work it out and your answer is 3, you're gonna say that your curve is mesokurtic, right? So it's not peaked, it's not flat. It's mesokurtic. If you obtain a value that's less than 3, that indicates flatness or platykurtosis. So you can describe that distribution as platykurtic distribution. If you obtain a value that's greater than 3, this indicates peakedness, or you realize that you can describe that distribution as leptokurtic. Now, as you can imagine, this is a little bit of a headache. And so what happened, the formula has been adjusted to include a -3. So they've added a -3 to the formula, and this helps to reduce the headache a little bit. So what happens now is that when you apply this new formula, what do you think is gonna happen? You're gonna get 0. The normal distribution will have a value of 0. Now this, yes?
But I assume that, let's say you have a normal distribution, you have a distribution almost normal. At what point is the cutoff? Because you can get like 0.08.
All right, we'll talk about it. We're gonna talk about it. Good question, we'll talk about it. So this latter definition is used so that standard normal distribution will, when computed, have a kurtosis of 0. When we use this second definition, positive values will indicate a peak distribution and negative values will indicate a flat distribution, because with the second formula, normal distribution is now at 0. Now, what I need to point out to you now is that there are different terms for the different kurtosis that we've just looked at. So whenever the adjustment is made The adjustment meaning the -3 is applied to the formula. The term that is used is called excess kurtosis. So these are the two terms. So the original formula with no -3, this one where 3 indicates a normal distribution, that one is called kurtosis, just kurtosis or kurtosis proper. The second one, where we've adjusted the formula, that one is called excess kurtosis or kurtosis excess. So you may see whichever term in the literature. Excess kurtosis or kurtosis excess. All right. Which definition of kurtosis is used is a matter of convention. So when you're using software to compute the sample kurtosis, you need to be aware of which convention is being followed. Many sources use the term kurtosis when they're actually computing excess kurtosis. SPSS uses excess kurtosis. What does that mean? Right, so that means that if you use SPSS to assess for kurtosis and you get 0 and you get 3, 3 means that what? It's peaked or it's leptokurtic. Very good. Again here, this is just repeats of positive values signal a more peaked distribution than the normal curve, and the negative values indicate a flatter distribution compared to the normal curve. So this is the take-home message. When you're assessing for normality, if kurtosis is okay and skewness is off, the data is not normal. If kurtosis is off and skewness is okay, it's not normal. You need both of them to be depicting the same thing, telling the same story in order for you to say the distribution is normal. So both of them need to be, to say zero, right, 0 if we're using the second convention. Good. Yes, we soon get to the question. All right. So we'll get to the question. This is just something I want to show you. You don't have to write it. It's really, I just thought it was very interesting. And I said, let me just share it. You don't have to write it. The formula for the mean is what? Sum of x divided by n. Standard deviation. Sum of x minus x bar. No, x bar. Come on. Why did I do that? X bar minus squared all over n minus 1. All square rooted. Perfect. Perfect. Even though it's okay. Maybe I should have used the variance. Let me use the variance. Just because I don't want you to miss what I have to tell you. Let's use the variance and get rid of this. The next one now is skewness. Skewness is the sum of x minus x bar over n minus 1 times s cubed, and that's cubed. and then kurtosis. X bar to the 4 n minus 1 times x to the 4.
Section that says the N and the I.
I mean, you don't have to. It's the same story. They're just kind of telling you more information. You don't have to stress. It's the same thing. What do you notice? The exponent here.
It's increasing.
Right. So that's what the math people would call the first moment, the second moment. Moment is something you guys met somewhere in physics, but no need to stress. I'm just pointing it out. Just FYI. It's just interesting. That's all. So we can see how things are going nicely. All right, so at this point now, we're gonna carry out some numerical assessments using SPSS. So get out your computers and we're gonna be using Moish Broad, which you already have. We're gonna be using Moish Broad database. Jody, you can share with Vanessa. Vanessa, can Jody share with me? I don't know that. Jody, share with you.
Twenty 2022, right?
Guys have Moish Broad up?
Not yet.
No. You should have it. You should already have it because we've used it up before. So students online, go ahead and open your Moish Broad. That's it.
find that one again? Just with a straight transit. You found it? Yeah. I went to one. Yeah, that was close. Yeah, before. Look for us.
Right, so are we ready? I'm not ready. I'm not. I am not. Oish, bro. Students online, are you ready? Have you found the Moish Broad?
Is it Moish Board 2022, miss?
Yes, that's right.
Okay, yes.
All right, good. I can't find it anywhere. It has to be there. It has to be somewhere. M-O-E-S-H. There we go. So Moish Broad is a data set that we are all familiar with. So the variables, questionnaire ID number, cluster number, locations, age category, marital status, union status, number of persons in household, number of children, the number of elderly, total monthly household income, industry group that they worked in, length of time they've been living in their neighborhood, their height, and finally their weight. So we are all familiar with this database. So right now we are asked to examine the kurtosis and skewness of our data concerning height in this data set. Now there are a number of ways that we could actually do this, but one quick way is this way that you have on your slide. So what we're gonna do is to go to Analyze, Descriptive Statistics, and then Descriptives. Then we're gonna transfer the variable height. We're gonna click on Options, and we're gonna tick off Skewness and Kurtosis. And we're gonna hit Continue and hit OK. So this is a quick way. So Analyze, Descriptive Statistics, Descriptives. The variable of interest is height. And we're gonna go on Options. And we're gonna tick off kurtosis and skewness. You don't need to untick what's already there. You can leave those. So what we're adding to the mix is kurtosis and skewness. Once you've done that, we're gonna click Continue, and then we're gonna hit OK. So this is our output. So our variable here, total height. Then we have the number of persons for which we have valid responses. 4,552. So the minimum, the shortest person is 3.3, the tallest 7.1. The mean height is 5.5. The standard deviation is 0.2, or let's say 0.3. Then we have the skewness. So for the skewness, we have the skewness statistic. So when they've applied the formula, this is the value that you've gotten for skewness. And then realize that skewness also has a standard error for itself. So there's the statistic, this is the answer when they've applied the formula. And then there's a standard error. And then we have kurtosis over here. This is the statistic. So SPSS uses the excess kurtosis formula. So this is the value that they've obtained. And the kurtosis also has a value for its standard error. So there's a standard error for skewness. There's a standard error for kurtosis. Now the skewness is 0.17. What is your impression of the skewness based on what we've done so far? So we were speaking about skewness needing to be 0 if our data is not to be considered normal. So 0 or close if our data is to be considered normal. I think this is close to 0. So 0.172, close to 0. What about kurtosis? 2.863.
Far from 0.
I think it's far from 0. So it appears to be a little bit more peaked than the normal distribution. So theoretically, that is the story. But we know that in the real world, things do not normally line up as nicely as we want them to do. So, what do we do? So what I'm saying is that the ideal thing is that skewness and kurtosis should be 0. Then we will know that our variable height is normally distributed. However, our skewness is 0.172, our kurtosis is 2.836. They are not 0, especially the 0.172, but it's close to 0. How skewed? So we now need to figure out how skewed is it really compared to a normal distribution. And similarly with the kurtosis, how peaked is it? How far off is this value from a normal distribution? So to help us with that situation and also to answer Jabari's question, what we have are rules of thumb that have been commonly applied throughout the literature. So this is one rule of thumb. If kurtosis and skewness are not between -2 and +2 inclusive, then the data is considered too far away from a normal distribution, and it needs to be corrected for before applying tests that have assumptions of normality. Some books, so some authors, they may say -1 to +1. So this is considered a more stringent criterion when normality is critical. Did you guys get bumped off? Students online?
We're still here.
Okay, all right. Thought I lost you for a minute. So this is the rule of thumb here. All right. If we were to apply this rule of thumb, what is the story?
We're highly peaked. We're not normal. That's why it comes back to the point where we
Both of them have to be saying the same story. So why is it not normal?
Because both criteria are met.
About what? The kurtosis is what?
It's peaked, it's outside of the range. It's basically
It's-
3.
It's basically 3.
Yeah,
Yeah.
the skewness is pretty much zero.
And the skewness is pretty much zero. So it's not skewed, but it's a little peaked. All right, it's a little peaked. But if you ask me, I will just keep going. But
So overall, Miss, we would say that it's still not normal. Because earlier you said if
so
one is
overall, if you're
close,
trying to be very strict, if you're being very strict, if you're being very strict and you know, things are not so critical, things are extremely critical, then we'll just say it's not normal by the -2 to +2 rule of thumb. But I mean, 0.8, if you ask me, if things are not all that critical, then it could work. But that is what we say when we have these numerical measures, they're very strict. And so sometimes things can pass as normal, but because of the rules, you just say, okay, it's not normal. But just looking at it based on the rules, we'll say it's not normal because the kurtosis is greater than +2. So it's a little bit peaked. All right. Here's another rule of thumb. This one says, we could look at the absolute value of the ratio of skewness to its standard error and of kurtosis to its standard error. If the value that we obtain is less than or equal to 2, then we can confirm that our distribution follows what? Or conforms to a normal distribution. So in computing this ratio, ensure that the standard error of the skewness and the kurtosis, ensure that you're using the standard error of the skewness and the kurtosis, which SPSS gave us in the output, and not the standard error of the variable itself. So you want to be careful of that. So if we should apply this to our example, let me go back. Let me see if I have it over here. If we should apply this to our example. So skewness divided by SE for skewness. This is gonna work out to 0.172 divided by 0.036. 4.78. And then kurtosis divided by the SE for kurtosis is gonna be 2.863 divided by 0.073. What did you get for this? 39.222. Okay, 22. Tell me. It's just a rule of thumb. You can tell me what you think. I know you're onto something. Go ahead.
I'm not up to anything.
Go ahead and tell me. Save me the trouble. I know you know. Just think back. Think back to the formula for the C test or T test. Any one of those things. So T is equal to, what was it? X minus mu naught divided by S over square root N. S over square root N is what?
Standard error.
Standard error. So it's very quick and easy, but in a sense, it's kind of like a little hypothesis test. And what do you think about the cutoff of the absolute value of 2? Take back to your Z table. Z alpha over 2 at 95% confidence interval. What is Z alpha over 2? 1.96.
0.96.
2. Right, almost 2. So it's kind of like, somewhere in that kind of story. All right, thumbs up. Okay, that's good. Good. So when we do this measure, so this measure, actually, this rule of thumb, let's say things are very critical and you want to quickly just assess for skewness and kurtosis. This measure would be a better measure than just looking at the values, the raw values themselves, right? So based on this, we're definitely gonna say that height does not conform to a normal distribution. Wonderful. All right, example number 2. It says, explore the data concerning height for persons from cluster 1 with regard to skewness and kurtosis. So now we need to select the cases. So only people who are living in cluster 1. So to select cases, we're going to go to data. And then the select cases option is towards the bottom. Second one up from the bottom. I'm going to click on select cases. And then right now it says all cases. So we're going to click the second option that says select if condition is satisfied. And then we're going to click on if. Cluster number. So we need persons who are living in cluster number 1. So we're going to transfer the variable cluster number over to the next side. And then equals 1. Cluster number equals 1. Generally, okay? Cluster number equals 1. Once you've done that,
Lost me at the if.
if, okay, let me go back. So you've clicked in here that says if condition is satisfied. Click on that. So you're gonna choose the second one here. If condition is satisfied. Then you're gonna click on if. You're with me so far? Juanita?
No, no, miss.
Are you seeing this if tab activated? Turns blue.
No.
Or maybe we need to go back from the start. All right, so data, you did that. Select cases, you did that.
Yeah.
All right. And then now you're seeing a little blue dot where beside all cases.
Hold on. Sort cases or select cases.
Select,
Sorry. I
select
was in
cases.
sort. Yes. Sorry, I was in sort.
All right, so go to select cases. Tell me when you're there.
Yes, I'm there. And then select.
All right, and then you see this word says select. If condition is satisfied, it means select. If condition is satisfied, click on that.
Yes.
And then you click on if.
And then the cluster.
And then cluster number, transfer that one equals 1.
Right.
Good. Once you've done that, you hit continue, and then you hit OK. And then we're gonna go to data view to make sure that we've done the right thing. So cluster number, good, stops at 76, case 76. So everybody else are in a different cluster. Good for us. So far, we have done the right thing.
Let's go back to analyze.
Mhm. So now, we want to assess height for persons in cluster 1. So we're gonna go to analyze.
Cluster number for me stops at 60.
60. Aye. Cluster did you put number 1? Cluster number equals 1?
Yes, I did.
All right. Mine stops at 76. I'm not sure what's going on with yours. Are you in Moish Broad 2022?
Yes, I am. Wait a minute.
Christian, how much is yours? How many persons do you have in cluster? 76? And then that is true. All right, monitor, let's go back. So go back to data.
Yeah.
Select cases.
Oh, no, sorry. You're fine. You're
It's
fine.
fine. You have 76 people
It's
in cluster
76.
1?
Yes.
Okay.
I just
All
needed to
right.
refresh it. Yeah.
Okay. All right. That's good. All right. So let's go now to analyze descriptive statistics and then descriptives. So the same steps. Analyze descriptive statistics, descriptives. And we still want to look at the variable height, but this time it's only going to be among persons from cluster 1. So height should already be there. Options, kurtosis, and skewness are already there. So all you need to do is hit OK. If you're just joining us and you weren't here for the first example, you're gonna transfer the variable height in the variables box. Then you're gonna go on options, click on kurtosis, click on skewness, hit continue, and then you hit OK. And I'll give you 1 minute to make your assessments. Ready? All right. When it comes to the variable height for persons in cluster 1, what's your conclusion concerning normality? just looking at the raw values for skewness and kurtosis. So skewness is 0.251. And 1.147 for kurtosis. We would say that it's normally distributed because both values fall within the -2 to +2 rule of thumb. All right, so if we look at the raw figures, the conclusion is that height for persons in cluster 1 is normally distributed. If we were supposed to look at skewness to its standard error, the ratio of skewness to its standard error, 0.279. No, that's not right.
0.251.
0.251.
Then 0.279.
251 divided by 0.279 works out to be what? 0.90. And then the ratio of kurtosis to its standard error is 1.147 divided by 0.552. So what did you get for this one? 2.08. What's your conclusion? Are you changing? Listen, this is 2. It's not like 2.5 or 2.6. Come on. Both of them, the absolute value will need to be less than or equal to 2. So right now, the absolute value of the ratio of skewness is 0.29. But even if you do, what are you gonna get?
2.1. One zero.
All right, so we're gonna conclude that height of persons in cluster 1 conforms to a normal distribution.
Has there ever been a scenario where you get different values in normality?
Because remember when I said in the first time, you see how this is 4 compared to if we just looked at 0.172, it wouldn't be skewed, but now we're seeing like, you know, a little bit of positive skewness there. All right, so the next 2 analysis technique for assessing for normality called Molgorov-Smirnov and the Shapiro-Wilks. For both of these tests, the null hypothesis is that the frequency distribution of your data conforms to a normal distribution. So the null is that, what's the null? Your data conforms to a normal distribution. The alternate, no, sorry. These tests, both of these tests will produce a P, which will assist us in determining whether or not to reject our null hypothesis. All right. So for both tests, both the Shapiro-Wilk and the Kolmogorov-Smirnov, if your p-value, so here it says a p-value smaller than your alpha, and we're just saying that the alpha is 0.05.
And that would be at the 95% confidence.
Right, so if your alpha is, if you get a value that is not smaller. So it says smaller than 0.05, no. Then we will not reject H0. And we're gonna conclude that normal distribution is assumed. If your answer to this question is yes, to this situation, so if your p-value is smaller than 0.05, so if that's yes, then what you're gonna do, you're going to reject H0 and you're gonna conclude that your data does not conform to a normal distribution. All right. Now, the Kolmogorov-Smirnov test is usually used for large data sets. Typically, data sets that are greater than or equal to 2,000. So we have 2,000 or more cases for whatever the variable of interest is that you want to look at. This test is also known as the KS-Lilliefors test. So you may see that in the literature, it's the same test. The Shapiro-Wilk test is used for smaller data sets or data sets that are less than 2,000. So we're going to use SPSS to assess for normality using these two new numerical techniques. So we're going to be focusing on the variable. This time we're going to go ahead and assess for normality, looking at the variable height and persons who live in cluster 1. Cluster 1, so we're going to start backwards. So since we've already selected for cluster 1, we've already there, we're just going to start there. So we're going to go to analyze descriptive statistics, and this time, instead of descriptives, we're going to go to explore. Then we're going to transfer the variable of interest, which for us, it's height. Then we have to go another step further. We're going to click on plots. Once you click on plots, you're going to tick off the option that says normality plots with tests. Then we're going to hit continue and then hit OK. What I'm trying to, okay, keep. So analyze, descriptive statistics, explore. It's right below descriptive. This time we're clicking explore. We hit explore. Still height, we're looking at height for persons in cluster 1, so our filter is still on. So the dependent list, height. Then we're gonna click on plots, And we're looking for normality plots with tests. So we hit that one. Normality plots with tests. Then we hit continue and we hit OK.
Hold on, wait for me.
Where are you?
Heights there.
Hmm?
Put cluster 1 in the label cases by?
No. The only thing you're transferring is height. Nothing else. Just height in the dependent list.
Oh.
And then you're gonna go on plots. You transferred height already?
Yes.
All right, so go on plots. So look on the right-hand side, you see statistics, plots, options, bootstrap. So click on plots. And then you're gonna look for normality plots with tests. You're gonna hit that one.
Okay.
Then
Okay.
you click continue and then okay.
Okay.
Matter of fact,
Yes. Okay.
we could just pick statistics alone, but it's fine. I think I'm gonna add that to the instructions. That is okay. Never mind. No, we can't do that. Let it be. It's fine. Result. Let's look at the output. So we have the Kolmogorov and we have the Shapiro-Wilk. Sorry, what's the conclusion? Where's the evidence for that conclusion?
For the Kolmogorov, the p-value is
So for the Kolmogorov Smirnov,
0.01, which is smaller, so it says reject.
so for the P, why is the eraser not working for this?
So that one is reject.
P is equal to point. What are you doing? I don't know what is that.
Smirnov.
Point 011. So
We reject.
so over here, one second there. So the output gives us the results for both the Kolmogorov Smirnov and the Shapiro-Wilk. So the section in yellow, we can see the results for the Kolmogorov Smirnov. So let's interpret that. So
Excuse
the
me.
p-value here. Yes, Nasha.
All right. Before you said that we use the Smirnov test when you have valid data set greater than 2000 or equal to, right?
I did.
But here we are using 70 something.
Mm-hmm.
So would you still use Smirnov here?
No. You should tell me, you should tell me.
No, miss. No. With that which was said before, I would use Smirnov here. I did that.
You wouldn't use the Smirnov here.
No.
So what are you gonna use?
Wilk. Shapiro Wilk.
All right. You are very much correct, but let's just look at what we have. But you're right.
Okay.
So the p-value for the Kolmogorov Smirnov is 0.011. Based on this p-value, what would our conclusion be?
You cannot assume a normal distribution here.
Right. So we would have to
Reject.
reject H naught. Reject H naught. The data does not conform to a normal distribution. Then if we looked at the Shapiro-Wilk test, the p-value is 0.074. This p-value is what? Greater than or less than 0.05.
Greater than.
So therefore, we will
Do
not reject H
Assume.
naught. And we are gonna assume, so normal distribution. Assume. So we end up with two different answers. So based on what Nashan reminded us, the appropriate statistic to be employed in this situation would be the Shapiro-Wilk test, because the sample size for this example was 76, less than 2,000. And if we applied this test, the conclusion is that our data concerning height for persons in cluster 1 conforms to a normal distribution. If we erroneously use the Kolmogorov-Smirnov test, the conclusion that we would make would be different. So that conclusion would lead us to something wrong, which you said, telling us that our data is not normal. Very good.
Can you go back, please, just a second?
Sure. Mhm.
What's the A at the bottom that says for the first and the first?
This one?
Yeah.
Because, yes, it does, you know. No, let me tell you. Lily 4 is for Kolmogorov-Smirnov. So if the sample size is smaller than what it should be, they're gonna add the correction there. But even with the correction, we're still not applying it there. Yeah. All right. Good. So some of this we've already said. That the Kolmogorov-Smirnov statistic is for larger sample sizes. The Shapiro-Wilk is for smaller sample sizes. So these tests, they basically tell you that your sample, whether or not your sample differs significantly from a normal distribution. And even these tests are very stringent. Like we said before, the numerical methods, they are very, very strict. So even if the deviation from normality is very, very small, it's gonna tell you that your data is not normal. That's one. Now, in some circumstances, both tests can produce misleading results. And in real world situation, or maybe I should say, statisticians or persons who are very experienced, they prefer to use graphical methods to help them in determining or, coming to a conclusion concerning normality. Simply because numerical methods are very strict. You're either normal or you're not normal, right? So statisticians, they like to look at the entire picture. So they'll look at the numerical methods, they'll look at the graphical methods, and then they'll come to a conclusion as to what is really going on. All right. So we're gonna go back again and we're gonna perform these tests, but this time we're gonna select all cases. We're gonna do this again and we're gonna select all cases. We're gonna go to data, select cases. Data, select cases, and then all cases. And then we're gonna click OK. Then we're gonna go to, now let's just check. Let's check first in data view that all the other clusters have been unselected. That's good. Analyze, descriptive statistics, explore. We're still looking at height. Still looking at height. Still looking at normality plots with test. Hit continue, hit OK.
We should click on the plot 2 after we have it height independently.
Click on what?
When it creates a thing.
If you should click on what, Vanessa?
Plot. And when we go select it, okay.
You go on plots, you click on normality plots with test.
Okay.
All right, good. So based on the Kolmogorov-Smirnov, what's our p-value? P is less than 0.001. And Shapiro-Wilk, P is less than 0.001. What's the appropriate text for us to use here? The Kolmogorov-Smirnov, and it's less than 0.001, so our conclusion is gonna be what? We're gonna be rejecting H0, and we're gonna conclude that our data is normal. Is not normal. So we're gonna conclude that our data does not conform to a normal distribution. All right. There is. Now this concludes our look at numerical summaries for assessing normality. So we've looked at skewness. We said that if our skewness is 0, then we know that our data conforms to a normal distribution. So skewness of 0 indicates normal distribution. A skewness less than 0 would indicate what? Our data is skewed to the left or left skewed. A skewness greater than 0 would indicate what? Positive skewed. Right. Kurtosis. So kurtosis refers to how peaked or flat our data is in comparison to a normal distribution. We said that if we're looking at kurtosis proper, then what? A normal distribution will have a kurtosis of 3. Values less than 3 would indicate flat negative kurtosis or flat distribution. And values greater than 3 would indicate peaked distribution, right? Now, we said that there's an adjustment because having that 3 tends to sometimes end up causing confusion. So to that formula, and -3 is added, which now changes the convention to say that a normal distribution will have a kurtosis of 0 while a flat distribution will have a negative kurtosis. Peak distribution would have a value greater than 0, positive value greater than 0. Good, so that's skewness and that's kurtosis. So we also looked at the Kolmogorov-Smirnov test. No, before we get to that, we looked at the rules of thumb for assessing those values, because we know that in the real world, things don't always line up. It's gonna be very hard to really just get 0 like that. 0.00 for Christian. It's going to be very hard to get that. And so statisticians employ different rules of thumb. So we said that generally, rule of thumb when looking at the raw values themselves is if the values for skewness and kurtosis fall between -2 and +2, then we could conclude or assume that our data follows a normal distribution. Some statisticians, if things are very critical, they may deviate from that rule to use -1 and +1. Then we said that another rule of thumb is looking at the ratio of skewness to its standard error, as well as kurtosis to its standard error. If these values, if the absolute value of these ratios are 2 or less, then we conclude that our distribution is normal, or data follows a normal distribution. If it's greater than 2, then it does not follow a normal distribution. And then the last tests that we looked at were the Kolmogorov and the Shapiro. Kolmogorov-Smirnov test and the Shapiro-Wilk test. For both of these tests, null hypothesis is that your data conforms to a normal distribution. They both produce a p-value. If your p-values are greater than your alpha value, then we're gonna conclude that our data conforms to a normal distribution. So this is just one of those cases where you do not want statistical significance. You know, we always want your data to be statistical. This is just one of those cases where you're just hoping that it's not statistical significance. All right, and if it's less than, then we're gonna assume that your data is statistically different from that of a normal distribution. We also said that the Kolmogorov-Smirnov test is appropriate for larger data sets that are greater than or equal to 2,000. The Shapiro-Wilk test is more appropriate for data sets that are smaller than 2,000. So that concludes our look at the numerical measures for assessing for new normality. The next thing that we need to do is to look at graphical assessments for normality, which we should have been doing today, but we're not going to do it in 15 minutes. So you'll get an early class. So next week, Friday, we're going to look at graphical measures for assessing normality. All the notes are there already. If you want to read ahead, you're free to do so. They're all here. No, I'll keep it for you in case you come next week and you left it. I'm doing it, you can have it. So it's there already. You can read ahead if you want to read ahead. Are there any questions? No questions. Okay. So see you guys next week, Friday.
Mrs. Chinbelly?
Yes, Nasham.
I sent you an email on Tuesday. Not pertaining to biostatistics though. I was enrolled in strategic resource, that course. And I don't understand why. Because I had selected only one course, which is operations management.
Okay, all right. I'll check it and let you know.
Your
I'll
email
check
is
on it
working.
and see.
Yeah, your email is working. Is your email working?
Yes, it's working. It's working. I'll check on it.
Which one?
Both of them are working. The U email and the Gmail are working. I'll check.
All right. Your telephone number working too?
Yes, but not WhatsApp.
Okay, I tried calling this morning, but I didn't get through. All right.
Oh, this morning. All right. Cool. All right, guys. See you on Friday.
All right, thank you. Have a great weekend.
Welcome. Thank you, Alicia. Same to you.
Bye-bye.
All right, bye. Thank you, Miss.
Bye. Bye, Kate. You're welcome.
Right, this is normal.